Good evening, everyone. So this is the lecture number 3 for the current electricity, right? Today in this lecture, we'll be discussing about the different arrangement of resistors. Particularly, we'll be discussing about the series combination and parallel combination of resistors, and then we'll be discussing about the mixed combination as well, where we'll be dealing with both series as well as parallel combination of the resistors, right? So let's start with the series combination of resistors of the circuit analysis, right? So the series combination of resistors, let's suppose here in this diagram, you can see that I have placed three resistors, right? I have placed three resistors, R1, R2, and R3. Three resistors, R1, R2, and R3. These are the three resistors placed in this fashion, right? And they are connected to a battery, and this battery is a closed one, right? And this is the switch here, and the switch is closed, right? And V is the potential difference supplied by the battery to this circuit, right? And let's suppose V1, V2, and V3 are the potential drops across resistors R1, R2, and R3, right? By series combination, we mean that if through two or more than two resistors, if through two or more than two resistors, the same amount or the same or equal current is flowing through them, right? Two or more than two resistors are said to be in series if the same current, right? You can see that the two resistors are in series if the current flowing through them is same, right? If the current flowing through them is equal or same, then we say that these two resistors or more than two resistors are in a series, right? So the basic concepts of about the series combination of resistors is that the current that flows through the resistors should be same, right? Then only we can say that the given resistors are in series, right? So in this diagram, in this picture also, you can see that this is a battery connected, right? And we have bulb here, right? This is the bulb glowing. And this circuit is a closed circuit, right? So there must be some current flowing through this circuit. Let's suppose I is the current, right? And this current, same current will be going through all these resistors, right? Same I current will be going through all these resistors and same current will be flowing through this bulb as well. So we can say that these three resistors are nothing. These three resistors are in series. In the same way, here in this circuit, you can see this circuit here. R1, R2, R3 are in series because if I is the current, if I is the current drawn by the battery, right? Drawn from the battery, and then same amount of current is going to flow through each of these resistors R1, R2, and R3, right? Where V1, V2, V3 are the potential drops across R1, R2, and R3, right? So what we want to do is that we can see that it's a series combination of resistors because R1, R2, R3 are having the same current through them, right? But we want to do we want to replace all these three resistors or more than three resistors, sometimes two resistors, right? Sometimes five resistors which are in series. We just want to replace all these circuits, all these resistors with a single resistor, right? Such that there is no change in the electrical effect or there is no change in the current flowing through the battery or drawn from the battery, right? So that resistor which is replaced in place of all these three resistors R1, R2, or R3, we call this as R equivalent or equivalent resistance, right? Equivalent resistance, right? So the equivalent resistance is nothing. It will produce the same electrical effect as is produced combinedly by R1, R2, and R3, right? So if we replace R1, R2, R3 with this R equivalent resistor, then the current or the electrical effect produced by the circuit will be same. It will not change, right? That's what do we mean by the equivalent resistance of a circuit, right? So let's try to see how we can replace a series combination of resistor with their equivalents, right? And you can see that I is the current flowing through the circuit and V is the potential drop provided by this battery. And this potential drop is distributed among three resistors here, V1, V2, and V3, right? So it means that this total potential drop is the V supplied by the battery, and this total potential drop has to be equal to V1 plus V2 plus V3, right? And we can see that V1 is nothing using the Ohm's law. V1 will be nothing. I is the current flowing through the R1. So it will be nothing. It will be I into R1, right? And similarly, V2 will be nothing. It will be equal to I multiplied by the R2 because I is the same current flowing through all these three resistors. And V3 will be nothing. It will be equal to I multiplied by R3, right? Now what we are doing is that we have just replaced these three resistors R1, R2 and R3 with the equivalent resistance, right? We have replaced them with the equivalent resistance, and this is the R equivalent, and same current. Here the current was also flowing I, and here the same current is flowing I, right? And the potential difference that was provided by the battery, it's once again the same, because we don't want to change the electrical effect, and we want to derive the relation for calculating the equivalent resistance for this circuit, right? So here in this case, if we talk for this circuit, this current, this potential difference will be once again V. That will be equal to I multiplied by the R equivalent, right? I multiplied by the R equivalent. Now we can replace this V, V1, V2, and V3 in this equation, right? In this equation, if we substitute the value of V, V1, V2, V3 in this equation, then V is nothing. It's equal to I multiplied by the R equivalent, right? That will be equal to IR1, right, plus IR2 plus I multiplied by R3, right? Or we can rewrite it as taking I as common, so it will be R1 plus R2 plus R3, right? R1 plus R2 plus R3, right? That will be equal to I times R equivalent, right? Now this I and I will get cancelled because this is the same current flowing through the equivalent circuit and same current flowing through the circuit before, right? So R equivalent is nothing. That will be equal to R1 plus R2 plus R3, right? So it means in case of series combination of resistors, what we have to do, we have to just we have to just add each and every resistance of a resistor so as to get the equivalent resistance of a series combination of resistors. So in this case, we can see that R1, R2, R3 are three resistors. Their equivalent is R1 plus R2 plus R3, right? So this is how we can find the equivalent circuit or equivalent resistance for a series combination of resistors, right? And we can also see that here we can also calculate this V1 as V1 is nothing, that's equal to I times R1, right? I times R1, right? Or I is nothing, that's equal to V upon R equivalent, right? I is nothing, I will be equal to V upon R equivalent, right? V upon R equivalent. So I will be nothing, VR1 upon R equivalent, right? That will be equal to V times R1 upon R1 plus R2 plus R3, right? That will be the potential drop across R1, right? Similarly, V2 will be equal to V times R2 upon R1 plus R2, right? Plus R3. And V3 will be equal to V times R3 divided by R1 plus R2 plus R3. So you can see that in these equations, the potential drop in case of series resistors, right? The potential drop in case of resistances which are in series, it actually depends upon the resistance of the resistor, right? Because the equivalent resistance for each for all of the resistor will be same, right? That's R1 plus R2 plus R3. So it means that larger the resistance of a resistor, greater will be the potential drop across that resistor, because the current flowing through them is same. So potential drop will be more for that resistor for which the resistance is more, right? So, or we can say that V is directly proportional to the R, right? In this case, because because I is same, right? I is same, right? It means that we can just tell this ratio V1 ratio V2 ratio V3 will be nothing. It will be equal to R1 ratio R2 ratio R3, right? So this is how the potential drops supplied by the battery will be distributed among the three resistors R1, R2, R3, right? And R V1 will be nothing. It will be V times R1 upon R equivalent, right? So let's suppose that if we have n number of resistors, if n resistors are in series, right? If n resistors are in series, then how can we find their equivalent? It means that let's suppose we have more than three resistors like this, and so on up to Rn, right? So this is R1, this is R2, this is R3. They are in series, right? Up to Rn. So their R equivalent will be nothing. Their R equivalent has to be equal to R1 plus R2 plus R3 up to Rn, right? Plus R, right? So this will be the equivalent resistance for n number of resistors, right? So let's suppose R1, each of these resistors are equal. That's R1 is equal to R2 is equal to R3, right? Up to so on is equal to Rn, right? So it means that we can just replace. We can just replace. It means that each the value of the resistance of each of the resistors is same, right? And the R equivalent has to be equal to, that will be equal to R plus R up to so on, right? Up to n terms, right? N terms. So it will be nothing. R equivalent will be equal to, in such case, equivalent will be equal to n times R, right? So this will be the R equivalent in that case, right? So in case of series resistors, when the two or more than two resistors are in series, the current flowing through them is same. Not only the current flowing through them is same, the potential difference provided by the or the supplied by the battery is distributed according to their resistances, right? Greater the resistance of a resistor, right? More will be the potential drop across that resistor, right? So let's discuss this very basic question here in this diagram, right? The question is that in the given circuit or in the given network, find out equivalent resistance of network. Also find out the potential drop across each resistor, right? So equivalent circuit for this network will be nothing. So R equivalent, you can see that if I is the current supplied by the battery, right? 3 amperes of the current is supplied by the battery, and this whole 3 ampere of the current is flowing through each of these resistors, 5 ohm, 2 ohm and 3 ohm, right? Then their equivalent resistance, because they are in series, their equivalent resistance will be 5 plus 3 plus 2, right? That will be equal to 10 ohm. That means that this is the equivalent resistance. So the equivalent circuit for this circuit will be nothing. It will be like this, right? It will be like this. So this will be the equivalent circuit. This will be the 10 ohm resistor, and this is the battery of 30 volt, and the current flowing is same. That's equal to 3 amperes, right? That's equal to 3 amperes. So this is the equivalent circuit for this series combination of three resistors. And similarly, we can find this V1. So V1 will be nothing. It will be equal to current flowing through R1 5 ohm resistor. That's 3 multiplied with the resistance of that. That's 15 volts, right? And V2 will be nothing. It will be equal to current. That's 3 ampere, and the resistance, that is 2. That's 6 volt. And V3 will be nothing. That will be equal to 3 multiplied by 3, that's equal to 9 volts, right? And you can see that this V1 plus V2 plus V3 together make total is equal to nothing, that's equal to 15 plus 6 plus 9, and they all together make total potential difference equal to 30 volts, right? 30 volts. That's the actual potential drop supplied by the battery, right? So this is how we can approach, how we can solve the circuits in series, right? Let's move on to the next concept. The next concept is about the parallel combination of resistors, right? In the similar fashion, the way we solved the parallel series combination of resistors, in the same way we'll be solving the parallel combination of resistors, right? You can see here we have three resistors, R1, R2, R3. They are connected in this fashion, right? And they are connected to the battery, directly to the battery, with the potential difference of V, right? Voltage or the potential difference supplied by the battery is V, right? And the current I has been drawn from the battery. You can see in this picture, current I has been drawn, and this I now here at this point will be distributed along three different branches. One current will be along R1, another will be R2, and third one will be along R3. So I1 is the current through R1, and I2 is the current through R2, and I3 will be the current flowing through R3, right? So once again, what we have to do is that we have to just replace these three resistors, R1, R2, and R3, with this equivalent resistor, so that there will be no effect on the net current flowing through the battery or net current flowing through the circuit. Or we can say that there will be no change in the electrical effects of a circuit. That's why we say this resistor as equivalent resistor, right? So now we will try to calculate the equivalent resistance of the parallel combination. And we know that for parallel combination, in parallel combination, all those resistors, we say that they are in parallel, or the combination is a parallel combination if the potential drop across each of the resistor is same, right? If the potential drop across each of the resistances is same, right, then the two resistors are said to be in parallel. Or we can say that each of the ends of the two resistor will be connected to the same point, right? Each end of the two resistor will be connected to the same point. In that case also the two resistors will be parallel, right? So if the two resistors, if each end of the two resistors are connected to the same point, you can see that for R1, the left end is connected to this point and the right end is connected to this point. For R2 as well, left end is connected to this point and right end is connected to this point, right? So you can see that these endpoints of each of the resistors are connected to the same point. We can say that these resistors are in parallel, right? And all these points, all these two endpoints of the each of the resistor are directly now connected to the battery. It means that whatever be the potential drop across the battery, same will be the potential drop across these resistors. So the potential drop across battery is V. So the potential drop across R3 will be V, right? And across R2 will also be V, and across R1 it will also be equal to V, right? So these are the potential drops across each of the resistors R1, R2, and R3. So these resistors are in parallel because you can see that each of the resistor is having same potential drop across them, right? But they will be having a different current if all resistors are different. If they are having different resistances, right, like R1, R2, R3, they will be having a different current flowing through them, right? Now our task is to find the equivalent resistance for the circuit, right? Potential drop for each of the resistor is same, right? You can see how, also in this diagram, right, where three resistors, right? These are the three resistors which have been shown in a color coded resistors, right? These are the carbon color coded resistors, right? This is actually how the resistances appear in the practical life or the in your laboratories. They are carbon color coded, right? They are color coded resistors, right? So we have different coding for different resistances. You can see here also in this diagram, we have different colors for the different coded resistors here, right? So that's how we do the coding for the resistors to calculate the resistances to know the resistance of a resistor, right? So you can see also here this is the battery, right? And this circuit is closed and the current, some current is flowing through the circuit here also, right? So in each of these cases, the potential difference across each of the resistor will be V, right? So let's try to evaluate how the equivalent resistance will be calculated for the parallel combination of resistances, right? We know that I current is supplied by this battery, right? And this I current has been distributed among R1, R2, and R3 as I1, I2, and I3. So the total current has to be equal to I1 plus I2 plus I3, right? And this current from this circuit, if we look at this circuit, the same current is I, right? We can write this I current as nothing that will be equal to V over R equivalent, right? That will be written as V over R equivalent, right? V over R equivalent will be the current through this circuit, right? And for this R1 resistor, if we write I1 using the Ohm's law, I1 will be nothing. It will be the potential drop across V across R1, that will be V upon the resistance R1, right? Similarly, I2 will be nothing. It will be V over R2, and I3 will be equal to V over R3, right? V over R3. Now replacing all these values of I, I1, I2, and I3, we'll get to know about the R equivalent, right? So we can replace I with V upon R equivalent, right? And I1 with V over R1 plus V over R2 plus V over R3, right? So this V and V will get cancelled, right? So which implies that our 1 over R equivalent will be nothing. That will be equal to 1 over R1 plus 1 over R2 plus 1 over R3, right? So this will be the equivalent resistance of each of the resistors. This is how we can calculate the equivalent resistance of a parallel combination of resistors, right? So it means that our in case of parallel combination, our one of R equivalent will be calculated like this, that the reciprocal of the R equivalent is sum of the reciprocals of each of the resistors, right? Each of the resistors, right? And let's suppose we have only two resistors in the circuit, right? These are the two resistors in a circuit. These are the two resistors in a circuit, R1 and R2, right? They are connected to some battery B, right? Like this. Their equivalent resistance will be nothing. For two resistors, R equivalent, 1 upon R equivalent will be equal to 1 over R1 plus 1 over R2. Or we can just cross multiply these resistors, we will get R equivalent as equal to R1 R2 over R1 plus R2, right? This is for two resistances, right? So for two resistances we can calculate equivalent resistance in case of parallel combination of resistors as R1 R2 over R1 plus R2, right? So let's move forward, and let's suppose that we have n number of resistors, then R1 upon R equivalent will be equal to nothing. That will be equal to 1 up over R1 plus 1 over R2, right? Plus 1 over R3 up to so on up to Rn resistors. That's 1 over Rn, right? And if R1 is equal to R2 is equal to so on Rn, that's equal to R, right? Then we can write equivalent resistance 1 upon R equivalent as equal to 1 over R plus 1 over R, right? Plus so on up to 1 over R for n terms, right? Or we can replace it with, so it will be n times 1 over R, right? It means that our R equivalent will be nothing. It will be equal to R upon n. So it means that in case of parallel combination, the total resistance actually decreases, right? In case of parallel combination, the total resistance of the circuit decreases, right? And this total resistance is always less than the smaller resistor, right? But in case of series resistances, in case of series combination, the total resistance of a circuit increases. But in case of parallel combination, the total resistance of a circuit decreases, right? It is always less than the smallest resistor, right? So you can see that here in this case, if n resistors of each of our of resistance R, then the equivalent resistance will be equal to R upon n, right? R upon n. And one more important point is that uh, uh, since potential difference is same for each of the resistor, right? Then the ratio of the current will be inversely proportional to the resistance, right? Current will be inversely proportional to the resistance, or we can say the ratio of the current for each of the resistance, that's I1 ratio, I2 ratio, I3 will be equal to 1 over R1 ratio, 1 over R2 ratio, 1 over R3, 1 over R3, right? So this is how the current will be distributed among three resistors R1, R2, and R3 in case of parallel combination of resistors, right? So this was it with respect to the series and the parallel combination of resistors. We will try to apply all these concepts, right, in some questions. Let's try to solve some of the questions related to these combinations of resistors, right? Let's start with the question number 1 here. So you can see in given network, find out equivalent resistance of network. Uh, also find out the current passing through each resistor, right? We have to find the equivalent resistance through this of this resistor, and we also have to find the current passing through each of the resistor, right? So we can see that the three resistors are in parallel, so their equivalent resistance will be nothing. Their equivalent resistance will be nothing. That will be 1 over R equivalent. That will be equal to 1 over 2 plus 1 over 3 plus 1 over 6, right? 1 over 6. So the LCM of 6, 3, and 2 will be nothing. It will be equal to 12, right? It will be equal to 12. LCM of 6, 3, 2 will be 6. Sorry, it will be 6, right? So it means that we'll take LCM equal to 6, right? So it will be 1 over R equivalent, right? So we'll have here 3, right? And we'll have here 2, and we'll have here 1, right? That's 3 plus 2 plus 1, that's 6, right? 6 over 6, that's nothing, that's equal to 1. That's equal to 1, or we can say R equivalent is nothing, it's equal to 1, right? That's equal to 1. That means that the equivalent resistance for the three resistors, 2 ohm, 3 ohm, and 6 ohm, here is nothing, it's equal to 1 ohm, right? So it means that we can just write this circuit in this fashion also, right? In this fashion also. This is a 1 ohm here, right? And this is a 24-volt battery. And if I is the current drawn from the circuit or the battery, we can write this I as V over R equivalent, right? V is 24 volts and R is 1 ohm. That's equal to 24 amperes, right? That's equal to 24 amperes. So this is the total current passing through the battery, right? If total current passing through the battery is 24 ampere, right? Now this 24 ampere current will come at this point, right? Through this battery, right? At this point, now this 24 ampere current will be distributed among three resistors, right? I1 will be through this, I2 will be through this, right? I3 will be through this circuit, right? Through this resistor, right? Through three branches, this 24 ampere current will be distributed. And if we find the current through the current through 2 ohm resistor, that's I1, that will be equal to, since we know that the battery is directly connected to each of the resistors, so potential drop across each of the resistor will be 24 volts, right? 24 volts. So the current will be nothing. It will be 24 over 2, that will be equal to 12 amperes. And similarly, I2 will be equal to 24 over 3, that will be equal to 8 amperes. And I3 will be equal to, that will be equal to 24 over 6, that will be equal to 4 amperes, right? 4 amperes. It means that the I1 will be I1 will be equal to 12 amperes, I2 will be equal to 8 amperes. We can write here it as 12 amperes, right? And it is equal to 8 amperes, and then we're left with 4 amperes, right? 4 ampere, right? If you add 12, 8 and 4, it will be once again equal to 24 amperes, right? So this is how we can solve this parallel combination of circuits, right? Using the concept of the equivalent resistances, right? So the current flowing through 2, 3, 6 is 12, 8 and 4 ampere respectively, right? So let's try to solve another question here. We can see on the screen there's a question, very important question. Two wires of equal diameters of resistivities rho 1, rho 2 and lengths L1 and L2, right? We have two wires, right? Let's make two wires here. This is the wire 1 here, and let's suppose this is the wire 2 with black color, right? This is the wire 2. Now these wires are joined together, right? They are joined in series like this, right? And the length, let's suppose length of this is L1 and the resistivity of this is rho 1. The length of this is L2 and the resistivity of second wire is rho 2. Now the question is that we have to find the equivalent resistance of the equivalent resistivity, not equivalent resistance. We have to find the equivalent resistivity for these two wires, right? So let's try to calculate the resistance of each of the wire, right? The resistance of each of the wire will be, let's suppose the resistance of this wire is R1. So this R1 will be nothing. It will depend upon the length, that's rho 1, L1, right? Since each of these resistors are joined together, they can be only joined together if their area of cross section is same, that's equal to A, right? They must be having the same area of cross section. If they have different area of cross section, then we will not be able to join them together. So they can be joined together only if they have the same area of cross section. So the area of cross section will be equal to A. Similarly, our R2 will be equal to, that will be equal to rho 2 L2 over A, right? And these two resistors are in series. It means their equivalent resistance will be equal to R1 plus R2, right? R1 plus R2. So replacing R1 with rho L1 upon A plus rho 2 L2 upon A, right? And let's suppose the equivalent resistance of these two resistors is like this, right? This is the equivalent resistor, right? And if this is the equivalent resistor, then the length of this equivalent resistor has to be equal to L1 plus L2, right? L1 plus L2, right? And area of cross section has to be same, that will be equal to A, right? So we can replace this R equivalent with here. Rho is the equivalent resistivity multiplied with the length, that's L1 plus L2, right? Upon the area of cross section, that has to be same A, right? That will be equal to rho 1 L1 upon A plus rho 2 L2 over A, right? We can just cancel out this A on both sides, right? So our rho equivalent here will be left with, that will be equal to rho 1 L1 plus rho 2 L2 divided by L1 plus L2, right? So this will be the equivalent resistivity of this series combination of the two resistors of resistivities rho 1 and rho 2 and lengths L1 and L2, right? So this will be the equivalent resistance or the equivalent resistivity for both the circuits, right? So let's move forward for further questions, right? Let's discuss more questions with respect to these combination, right? We have another circuit here. You can see in this circuit, we have to find the equivalent resistance of network and also potential difference across each of the a resistor, right? We have to find the equivalent resistance as well as the potential difference across each of the resistor, right? We can see here we have four resistors, 2 ohm, 3 ohm, 6 ohm, right? And we have this 3 ohm here, right? So we can see that 2 ohm, 3 ohm, and 6 ohm are the three resistors which are in parallel, right? They are in parallel. They are in parallel combination, right? So their equivalent resistance will be nothing. Their equivalent resistance has to be equal to 1 by 2 or 1 by 3 plus 1 over 6. That will be equal to 1, right? Their equivalent resistance will be equal to 1. So it means that we can just replace these three resistors with 1 ohm, right? We can replace them with 1 ohm and the same battery will be there, right? The battery will not change, it will be same. It will be a 24-volt battery, and these three resistors have been changed, replaced with 1 ohm resistor with their equivalent, right? We have 3 ohm resistor here, right? And let's suppose I current is flowing through the battery, right? Now these two resistors, you can see that now 1 ohm and 3 ohm resistors are having the same current I flowing through them. So we can say that 3 ohm and 3 ohm and 1 ohm resistor are now in series, right? They are now in series. So their equivalent resistance will be equal to 3 plus 1, that will be equal to 4 ohm, right? We can replace them with the 4 ohm resistor, right? 4 ohm resistor, let's write here 4 ohm, and this is a 24-volt battery, and I is the current flowing through them, right? If I is the current flowing through them, we can just write I as 24 over 4, that will be equal to 6 amperes, right? If 6 amperes is the current flowing through them, so 6 ampere will be the same current flowing here, and this 6 ampere will be the same current flowing here, and this 6 ampere will be the same current at this point here, right? Now this current will be distributed among 2 ohm, 3 ohm, and 6 ohm, right? We have to find the potential difference across each of the resistor, right? If this 6 ohm will be distributed here like I1, I2, I3, right? I3. And we can see that through this 3 ohm resistor, the current is also flowing equal to 6 ampere, right? So the 6 ampere current is also flowing here, right? If the 6 ampere current is flowing here, it means the potential difference across this 3 ohm resistor will be equal to, that's V equal to IR. The current is flowing, the current that is flowing is 6 amperes and the resistance is 3 ohm. So it will be 18 volts, right? It will be 18 volts. So it means that the potential difference across this 3 ohm resistor will be equal to 18 volts, right? And the total potential supply by the battery is equal to 24 volts, right? This is a 24 volts battery potential voltage supply by the battery, and the from this 24-volt battery, 18 volt is across the 6 ohm resistor. Then we're left with 24 minus 18, that is 6 volt, right? It means that 6 volt resistor has to be equal, 6 volt potential difference has to be equal to across this 1 ohm resistor, right? And this 1 ohm resistor is the equivalent resistor of this 2 ohm, 3 ohm, 6 ohm. It means that each of these 2 ohm, 3 ohm and the 6 ohm resistor will have a potential drop of 6 volt each, right? 6 volt each. So it means that across 2 ohm, 3 ohm and 6 ohm, the potential difference will be equal to 6 volt each, right? 6 volt each. So that's how we do this circuit. We solve this circuit, right? We use the both concepts here. First of all, we use the concept of parallel combination. Then we use the concept of series combination to find the total current. And from there, we calculate the potential drop across each of the resistors, right? So let's discuss another question here, right? You can see in this diagram, we have a circuit like this. We have to calculate the equivalent resistance across A and B, right? We have resistors like R, and these are the resistors here, right? These are the resistors here. This is the how these resistors have been arranged, right? But we have to calculate the equivalent resistance across A and B, right? We have to calculate the equivalent resistance across A and B. We have to calculate the equivalent resistance across A and B, right? So it means that if we have to calculate the equivalent resistance across A and B, then what we will do is that we'll just connect a battery across B like this, right? Battery of B potential difference will be connected across A and B. Then we'll try to solve this circuit, right? So we can see that here to for the circuit, for the complete circuit, to flow to for the current to flow through the circuit must be closed one, right? But we can see here, if we can see here, if we look at the ends of this circuit, right, towards C and towards D, we can see that we have two resistors. This is R and this is also R, right? We can see that these two resistors are open, right? They are open resistors, right? Open. If these two resistors are part of the open circuit, they are not the part of the closed circuit, it means that there will be no current flowing through these two resistors R and R, right? If there is no current flowing through these two resistors, right, if there is no current flowing through these two resistors R and R, it means that we can just remove them from the circuit, right? Remove them from the circuit. So there is no purpose of these two resistors, right? Remove them from the circuit, right? We can just easily remove them from the circuit, right? Because they are the part of the open circuit, right? They are not the part of a closed circuit. So it means that our equivalent circuit will be just reduced to this circuit, right? It will be reduced to this circuit. So this will be the new circuit here, right? So these two are actually removed, right? We can just remove these two, right? We'll be left here with R, 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 and each of them is having a resistance equal to R, right? Now you can see that here in this circuit, we have just reduced this circuit, removed these two resistors R and R. And this is our equivalent circuit, right? This is our equivalent circuit. You can see that if the current I is flowing through this circuit, and this current I will approach this point, what we call as junction, right? Some part of the current will flow like this, and some part of the current will flow like this. This is how the current will be distributed, right? And we can see that this I1 current will flow through this resistor, and this I1 current will flow through this resistor, and this I1 current is also going to flow through this resistor. And now again, these two I1 and I2 will join here, and this I1 current will leave this junction here, right? So it means that these three resistors are in series, right? If these three resistors are in series, we can just write their equivalent in this circuit, right? So these three resistors will be in series. So we can write their equivalent. Their equivalent will be nothing. That will be equal to R plus R plus R. That will be equal to 3R, right? So this is 3R. This is R. This is R, and this is also R. So this is the V battery, right? Now you can see clearly that here in this case, uh, R and 3R are now parallel to each other, right? If R and 3R are parallel, then their equivalent resistance will be 3R multiplied by R upon 4R, right? So that will be equal to 3R over 4, right? So we can just replace these two resistors with 3R upon 4, right? So let's write here 3R upon 4. It will be R here, it will be R here, right? This is the battery B, right? Now we can see all these three resistors are now in series, right? All these three resistors are now in series, right? They are in series. So their equivalent will be nothing. Their R equivalent will be nothing. That will be equal to R plus 3R over 4, right? That will be 2R plus 3R over 4, or that will be equal to 11R over 4, right? So this is the equivalent resistance, or we can say that the equivalent resistance for this circuit is nothing. That's equal to 11. That's equal to 11R upon 4, right? So this will be the final equivalent circuit, right? 11R upon 4. So this is the battery, right? This will be the equivalent circuit, right? This will be the equivalent circuit, right? So this will be the equivalent circuit or the equivalent resistance for this circuit, right? Let's move on to the next question. The question is that we have been once again given the circuit, right? You can just look at the circuit. The circuit is like there are many resistors in the circuit. We have to find the equivalent resistance of the circuit across the ends of this battery, right? Now you can clearly see that these three resistors are in series, right? 4 ohm, 4 ohm, and 4 ohm, right? If we just replace these three resistors with a single resistor, that will be equal to 12 ohm, right? 12 ohm. And similarly, these three resistors are once again in series. We can also replace them with the 12 ohm resistor, right? 12 ohm resistor. So our circuit will be reduced like, and you can also see that these two resistors are also in series. These two resistors are also in series. We can just replace them with 4 ohm, and we can also replace these two with 4 ohm, right? 4 ohm resistor. So it means that we have a circuit like this. This is the battery. This is the battery here. And this will be the 4 ohm because of 2 ohm and 2 ohm, that will be equal to 4 ohm. And we will have on the right hand side 12 ohm, right? And on the left hand side once again 4 ohm, and then we'll be having here 12 ohm, right? So see how circuit we have reduced this circuit to few resistors only, right? Now you can see that 12 ohm, 4 ohm, 4 ohm, and 12 ohm, they're once again in parallel to each other. So their equivalent resistance will be nothing. 1 upon R equivalent, that will be equal to 1 over 12 plus 1 over 4 plus 1 over 4 plus 1 over 12, right? So it will be equal to 2 over 12 plus 2 over 4, right? But that will be nothing. That will be equal to 12 will be the LCM, right? 12 will be the LCMs. It will be 2 plus 6, right? 2 plus 6. So it will be equal to 1 over R equivalent. That has to be equal to 8 over 12, right? 8 over 12, or R equivalent will be equal to 12 over 8, or we can write it as 4 over 2, right? Sorry, 3 over 2. 3 over 2 ohm, right? So 3 over 2 ohm will be the final equivalent resistance for this circuit, right? So the equivalent resistance for this circuit is nothing, but we have to calculate the current supplied by the battery, right? So the current supplied by the battery will be nothing. The potential drop supplied by the battery, that's equal to, you can see here that was equal to 16 volts, right? 16 volts. The current supplied by the battery will be nothing. 16 volts upon the resistance, equivalent resistance of the circuit, that's 3 over 2. So it will be nothing. It will be 30 over 32 over 3 amperes, right? So this will be the current supplied by the battery, right? This will be the current supplied by the battery in the circuit, right? Now let's try to understand about the new concept, what we call as concept of short circuit, right? So what actually is concept of a short circuit? Let's suppose we have this resistor here. These are the two this is the resistor here, right? This is a single resistor here. And what we are doing is that the two ends of these resistors are connected by this connecting wire like this, right? They're just connected by this connecting wire like this. It means that whatever be the potential here at this point, the same will be the potential at this point as well, right? If the potential at the 2 points of these connecting points is same, right, it means that the potential difference delta V will be nothing. That will be equal to V minus V. That's equal to 0, right? If that's equal to 0, then the current flowing through this resistor, let's suppose that's I, that will be equal to V over R, and V is equal to 0, that will be 0 over R, that will be equal to 0. It means that here through this resistor, if this resistor is shorted like this, right? If this resistor is short between the 2 points A and B, then the current flowing through this resistor will be equal to 0, right? There will be no current flowing through this resistor, right? If there is no current flowing through the resistor, we can just, in that condition, we can just remove those resistors or the resistances which are short circuited from the circuit, right? We can just remove them from the circuit because there is no current flowing through them. So they will not be a part of the circuit, right? So the current is 0 because the potential at the 2 points becomes same, or we can say the potential difference between the 2 points in case of short circuited resistor becomes 0, right? And the current through them also becomes 0. So this is the concept of the short circuiting of a resistor, right? So let's apply this short circuiting to some of the questions here, right? You can see that if circuit is short circuited between A and B, so we have 2 points here. It's short circuited between A and B, right? If this is short circuited between A and B, it means that between A and B, these are the short circuited points, right? Let's suppose I is the current flowing through this circuit, and once this current reaches this point A, now this is the short circuited path is here. This wire here is a zero resistance wire, right? This is a zero resistance wire, right? zero resistance wire. This is a zero resistance wire here, right? So it means that if this is a zero resistance wire, it means that the current flowing through this resistor will be equal to zero, and through this resistor also the current will be zero. It means that these two resistors will not be a part of circuit. These two resistors we can directly remove from the circuit, and the current will be only flowing like this. There will be no current through these two resistors, right? There will be no current through these two resistors, and we can just remove these two resistors from the circuit, right? Right, and only the current will be flowing through these two resistors R and R. Then the total resistance we can see, this is these two resistors R and R are in series. We can just add up the two resistances, that will be equal to 2R, right? That will be equal to 2R, right? That will be equal to 2R, and the potential difference is V. Then the current is nothing, that's equal to V over 2R. This will be the current flowing through this short circuited circuit, right? So this is how the short circuit plays a role, right? So when a resistor is short circuited, you can see that here clearly we have two resistances which are short circuited, right? This R and this R, they're short circuited, right? So if they are short circuited, then there will be no current flowing through them, right? Let's discuss one more question here, right? It's with respect to the short circuiting as well, right? The question is that find out equivalent resistance between A and B, right? Once again, we have to find the equivalent resistance between A and B. This is a short circuited circuit, right? Now you can see here we have two resistances which have been short circuited here, right? This resistance between C and C, this resistance between C and C, it's once again short circuited between these 2 points, right? It means that we can just remove this resistor from the circuit, right? We can just remove this resistor from the circuit. And one more resistor, you can see that that's short circuited in this circuit. This resistor, right? You can see between this point and this point, this resistor is also short circuited. We can just remove this resistor from the circuit, right? Then we're left with three resistors like this. This is R, this is R, and this is R, right? This is the point A, this is the point B, right? And we can just write these two resistors are in parallel, right? They are in parallel to each other, right? Their equivalent resistance will be nothing. That will be R over 2, right? It means that this equivalent circuit will be written like this. This is R over 2 and this is R, right? And this R over 2 and R is once again in series. It means that R equivalent will be nothing. It will be R plus R over 2. That will be equal to 3R over 2. So this will be the equivalent resistance for this circuit, right? For this short circuited circuit, we have the equivalent resistance equal to 3R over 2. So it means that if the resistor is short circuited in the circuit, we can just remove that resistor because the current flowing through that resistor will be equal to 0, right? So we'll stop here, and in the next lecture we'll be discussing about the Kirchhoff's law, right? And we'll be applying Kirchhoff's law in solving many other circuits as well, right? So let's stop here and see you in the next class. Till then, take care and goodbye.